Hopefully by now you've had quite a bit of practice with balancing equations and also with calculating formula mass and molecular mass of compounds. We're going to tackle the mole today and determining molar mass. To me, the mole is one of the quintessential things of chemistry. If you don't know what a mole is, I unfortunately graduated high school taking high school chemistry, and yet when I went to college not knowing, really understanding what a mole is. So I want to make sure that you don't finish this course without really understanding what a mole is in chemistry, when it's just a term that's used to say a number. So let's go. And then we're going to talk some about empirical formula and percent composition. This is beast, that empirical formula from percent composition, that gives students the most trouble. So we're really going to work on that, and I'm probably going to do some just of my own videos. I don't know how you guys like those, but I think that they're necessary, so we're going to tackle those. All right, here we go. I want you to know what a mole is. If I asked my husband to go to the store and get a dozen eggs or a dozen donuts, he would go and get me 12. We know that. If you were a person that knows anything about fireworks and you went and got a gross of bottle rockets, you would get 12 dozen, which is 144. That's what's in a gross. A ton. Everybody knows, or most everybody knows, what a ton is. I have a ton of papers to grade. Well, that's 2,000 pounds. And by the way, guys, that's literal. I probably have close to that many papers to grade. So these kinds of things, we're used to that. But atoms are so small that it's ridiculous for me to ask you to go get me a dozen atoms of hydrogen or a dozen atoms of oxygen. We can't even see an atom. They're way too small. It's way too small to even conceive of going and getting a dozen of this, or even a gross of atoms of carbon. Can't do it. Can't see them. So we got to come up with a number that's significantly larger. And the name that was come up with to represent the number of atoms is the mole. And there was a Italian dude, his name was Avogadro, and so it's called the Avogadro's number. And that number is called a mole. And it's an extremely large number. It's 6.02 times 10 to the 23rd. Now let's put that in perspective. Most of you know what 1,000 is. We seldom have $1,000 in the bank. We might owe $1,000, but we seldom have that much money in the bank. Some of us aspire to having $1 million. This is 1 times 10 to the 6th. Okay? That's a 1 with 6 zeros behind it. Let's think about how many is going to be 23. That is 602 heptillion. Heptillion. So put that in perspective for you. There's a million, 2 sets of zeros behind there. Hepta means 7. So you're going to have 7 sets of zeros after that 602. That should put it in perspective. That's how many atoms that if I were to ask you to go to the store and buy me a mole, or to get me a mole of eggs, that's how many eggs you'd bring me back. 602 heptillion. And that would not even fit in a shopping cart or even a car. So think about that. That's a lot. All right. But it's not a lot when it comes to thinking about something that are as small as atoms. So that's exactly what we're talking about. And so since that would be a lot to count, and it would take you a long time to count 602 heptillion. We seldom count that many particles. Instead, we use other ways to convey what we mean by 602 heptillion. So, Avogadro's number is one way, 602, 6.022222 times 10 to the 23rd, which we're usually going to round off to 6.02 or 6.022. That's a typical way to say it, times 10 to the 23rd, of course. Avogadro's number. And then here are some conversion factors. All I really want you to learn, though, is that top one. If you know that top one, then you can use it as a conversion factor in dimensional analysis problems. So this chapter, the rest of this chapter, is going to be extremely heavy in conversion factors. And there are going to be 3 conversion factors that I'm going to ask you to learn. And those 3 conversion factors that I'm going to ask you to learn are going to be the 1 mole is equal to this Avogadro's number, 6.02 times, or 6.022 times 10 to the 23rd of any object. Also, that 1 mole is equal to a molar mass, which we're about to get to. And I'm also going to ask you to learn very soon that 1 mole of anything is going to be equal to 22.4 liters for gases. And we're going to talk about that later as well. But let's recap, how do we solve dimensional analysis problems? To solve dimensional analysis problems, do you remember what to do? We're going to write our given. We're going to write our unknown. Write your given. We're going to work a sample problem here in a minute. You write what your unknown. There's never ever going to be a number in your unknown. Never. Only your units. And then this would be a conversion factor. This on one side and that on the other. Okay? And then we can solve it. And you always solve by starting with your given. Always. All right? Now then, let's look at this one. Typical human body has 30 moles of calcium. 30 moles of calcium. So let's solve this as if you would solve it. We're going to say 30 moles of calcium. And it's asking us, that's our given. Well, let me write it as a given. Our given is 30 moles of calcium. Please write your symbols correctly. What's our unknown? Determine the number of calcium atoms. So our unknown is the number of atoms of calcium. Our con factor that we're going to use is for every 1 mole of calcium, there are 6.02 times 10 to the 23rd calcium atoms. That's my con factor that I'm going to use. And you need to know that. How did I know that it was going to be an atom and not a molecule? I know that because calcium is an element. And since calcium is an element, I know that my smallest piece of an element is an atom. So I'm ready to solve. And I'm always going to solve by starting with my given. My given is this 30 moles. So I'm going to put that 30 moles of calcium, and that's going to go over my 1, or over, if you have to put your little smiley face or whatever. And since moles of calcium is on top right here, I'm going to put my moles of calcium, and remember where those come from. They come from your con factors. I'm going to put that in the denominator. I'm going to put the moles of calcium. For every 1 mole of calcium, I have 6.02 times 10 to the 23rd atoms of calcium. Now that mole takes out that mole. See that mole of calcium right there. That mole takes out that mole. And now I'm going to multiply across the top. I'm going to say 30. I'm going to use my trusty calculator. And I'm going to say 30 times 6.02 times 10 to the 23rd. Please remember, when you're using a scientific calculator and you put something in, I'm going to show you in just a minute what you need to put in your calculator. Please don't hit the times or the 10 when you're putting an exponent in your graphing calculator. I've got 1.8 times 10 to the 25th atoms. Now, please notice of CA, I was careful with my significant digits. Okay? Oh, this one has, I'm going to go back then. My given here, it says, is 30.0000, so I have 4 sig figs. So I'm able to put 1.806. I can put one. Your given is what determines how many sig figs, and my given should have actually been 30.00 moles. So I can leave my 1.806 atoms of calcium in my answer. Now, I would like to show you exactly how to go about putting this in your calculator. To put this in your calculator, I'm going to show you the buttons that I pushed on the calculator. I hit the 1. Well, actually, I hit the 6. I hit the times. I'm sorry. I need to go back. When I had this set up, I had 30.00 mole of calcium. And I had this right here. I had, for every 1 mole of calcium, I had 6.02 times 10 to the 23rd atoms. When I entered this in the calculator, I entered 30.00. Then I hit times. Then I hit 6.02. And I did not hit times. For this times right here, I did not hit times, and I did not hit 10. I did not. I did not enter a times. No. Instead, I entered the second button, the blue button on my calculator. I have a TI 84. I hit the blue second button. And then right above the 7 is the comma, which says EE in blue, because I hit the blue shift, the blue second button. I'm looking at the blue numbers and it says EE. That EE stands for exponent. Okay? And then I entered in 23 for the 23rd power. And then I hit in enter. I never put a times or a 10 right there, because you will be off by a power of 10 if you do. And then my answer that I got said 1.806 E25. That E right there means times 10 to the. So I knew when I put my answer, I needed to record it as 1.806 times 10. See, I put it in there to the 25th power. That E means times 10 to the 25th. So make sure that you get that. Okay. And then here's how A is worked out. And then letter B in your example problem that's in your textbook for you. This is sample problem 3.5, as you can see from the slide. I didn't tell you the page number. I apologize for that. This is on page 91. Letter B asks you for the number of moles. If it gave you atoms, how many moles would that be? So you can see from this slide, now my given is in atoms. So can you see that the conversion factor is going to be flipped upside down? So now you're going to divide. And now it comes even more vital that you enter that EE 23rd correctly, or you're going to be off. Your answer is going to be off significantly. All right. Now, the next slide's talking about, well, you know what? I'm going to stop right there because we're going to the next section. So I'm going to let you practice those. I'm going to start another video right away.